Um, Hello, am I audible? Can someone please confirm?
Yeah, ma'am, you're audible.
Okay, I'll also like to quickly share my screen and check.
Yeah, ma'am, you can share your screen.
Yeah, so can you see the screen along with the pointer?
Yes, ma'am, we can.
Okay, okay, sure.
Yes, ma'am, you're audible.
Good morning, ma'am.
Yeah, good
We'd
morning.
like to give a short intro and then we can proceed.
Yeah, works fine.
Yeah. One second. Maybe we should wait a few more minutes for participants to join in.
Yeah,
Yeah, please wait like 2 minutes more.
yeah, sure, sure.
Thank you. I think we should start now without delaying any further time. Thank you all for joining for this session. This will be the last session for our uh, X-ray astronomy. Welcome our speakers, that is Dr. Shama and Dr. Netra. They both are part of the Space Academy group at the UR Rao Satellite Center. They are esteemed scientists with the specialized X-ray astronomy. Their work pioneer on utilizing the lunar platforms for X-ray observations, offering unique perspective and opportunities to study the universe. Their research has been instrumental in advancing our understanding of X-ray emission and their sources, leveraging the moon as a vantage point for astronomical observations. In this workshop, presenting X-ray astronomy from the moon, sharing groundbreaking insights into this innovative approach to space exploration. We are very fortunate to have them as our speakers as they share their insights in this session. Thank you.
So could I start?
Yes, yes, please.
Yeah, so good evening, everybody. This is Netra here, and I'll be talking about how we are using X-rays to study the actual surface composition of the moon. So there's just a slight change in the title. It's not X-ray astronomy from the moon. What we are interested in doing is how do we use the X-ray emissions coming from the moon to study its surface composition. So this is tending more towards planetary science and its applications. So to begin with, a short introduction. So The first question that we have to ask is, what do we know about the moon and how do we know all of these things about the moon? So currently we have a very good understanding of the theory behind the formation of the moon, which is the giant impact hypothesis. What this essentially means is that a mass-sized object called Theia, it collided with the proto-Earth. So we are referring to the Earth at the very early stages of the formation of the solar system. So where everything is still in the gaseous as well as molten stages, and things are sort of accreting together, and most of the earth is pretty molten in nature. So in this scenario, when we have such a collision, what tends to happen is that there is a lot of debris from the earth which is propelled outwards, and it forms the sort of an accretion disk like thing around the earth. And it is from these fragments that the moon is known to have coalesced. Now, there are multiple lines of evidence why we suspect that this has happened, primarily due to the isotopic ratios of both the samples from the moon as well as the terrestrial samples. So, what we understand is that the isotopic ratios of multiple elements are similar between Earth and Moon, which gives us the clue that they might have formed from the same material. And we also see, based on kinetic energy, momentum calculations, etc., that the most accepted theory for the formation of moon is the giant impact hypothesis. But the history of moon doesn't really end here. What happens then is that because this collision is such a large scale collision, it led to the formation of what is called a global lunar magma ocean. So the moon was essentially completely molten, and we had various minerals crystallizing out from this molten magma. So shown here is the sort of unmelted interior core, which is very rich in iron and other heavy elements, and the rest of the molten magma surrounding it. From this magma, you had first the crystallization of iron and magnesium rich minerals, which are known as olivine. And later, as the temperature cooled further, you had various other phases that were forming. For example, pyroxene. And finally, you also had these lighter minerals which are rich in calcium and aluminum, which were crystallizing from this magma. And since they were less dense, they tended to float upwards. And whatever floated upwards forms the primordial highland crust of the moon. Finally, in the last stages of the evolution of moon, you had some leftover molten material which was enriched in these incompatible elements called creep, which are potassium rare earth elements. So these are also rich in radioactive elements, and it has known to be the source of further volcanism on the moon. Post this was a history of impact where you had a lot of large scale collisions that happened on the moon. So if we see the moon in our night sky, we know that it is not completely bright. In fact, it is marred by these dark patches on the moon, which are called the mare regions. These mare regions are formed as a result of volcanism. So what essentially happened was that you had a lot of these impactors which were roaming around in the early solar system, which have come and impacted this highland crust of the moon, excavated the inner layers of the mantle, which are rich in these iron, titanium, magnesium rich minerals, and are also darker in color. That molten magma came upwards, which is volcanism, and then crystallized to give these darker regions, which are called as the mare regions of the moon. And this impact history has existed for a very long time in the lunar evolution. Current estimates are that this process occurred for about 3.9 billion years ago till 2 billion years ago. So currently, moon is not very volcanically active, is our understanding, but it had a very rich history of volcanism. So the next question that we need to ask is that, given that we know all of this from the moon, how did we really come to these understanding? So there are three major kind of data collection that we can use to study the moon. The first being in situ experiments. Now, these are generic techniques which can be true for any space-based mission. So in situ experiments are those which are housed on landers or rovers, and they take direct measurements from the lunar surface. So through these, there can be a variety of techniques which can be applied, and a range of science questions can be addressed. For example, in the Apollo era, there were a lot of seismometers that were taken to the moon and placed on the surface of the moon, and they tell us about the moon quakes, which basically helps us understand a little bit about the interior structure of the moon, whether is there any kind of tectonism that's happening, is the crust uniformly thick on the near side as well as far side. So these were the kind of questions that you can target with an experiment like a seismometer. There were also spectrometers that were taken, which did in situ experiments. For example, one of the Apollo missions had an X-ray fluorescence spectrometer, which studied the uh, elemental abundance of the lunar soil. So these are the kind of in situ experiments that are possible to do. The second, and as you may all know, taking something from here and then actually performing these experiments on the surface of the moon and then transmitting all that data and processing on the ground is a pretty expensive affair. Similarly, such an expensive experiment to do would be sample return missions. So we've had samples that have been returned from Apollo missions, Luna missions, and more recently, even the Chang'e mission. So currently, there is a repository of almost 400 kg of lunar samples that have been collected from the equatorial regions in the time of Apollo missions. There have also now we have samples from the far side of the moon from Chang'e too. So the advantage of doing a sample return mission is that you can perform very high precision and measurements on it once the samples are returned back to the Earth. So you know that in labs these days we have very high precision instruments like SIMS, XRD, etc., which can actually give you precise information about the science question that we're targeting. But keep in mind that sample return missions require a lot of complicated technology, which involves taking either man or robotic technology to the surface of the moon, actually collecting the samples. So that also requires us to land and then lift off from the moon and then safely re-enter the Earth's atmosphere and retrieve back the samples and then perform the experiments under various conditions. However, the most cost effective way of studying is remote sensing missions. So that is like the easiest technique that has been applied all the way from sun to even our outer solar system planets, because you can carry instruments on orbiters which go around the surface of your planetary body of interest. It could have cameras which can take images of the surface. It could have spectrometers in bands starting from X-ray all the way till IR, which can study the emissions, reflectance, etc., from different portions, and then gives us a sort of holistic picture of the complete planetary body. So while it is cost effective, it also helps us give a complete picture from afar, and therefore it can gives us it is the most like it is the first technique that is applied to study any planetary body. So now coming to the technique that we in our group at our space astronomy group in URO Satellite Center, the technique that we work on is called X-ray fluorescence spectroscopy. The physics behind this is as follows. So we have an atom with the nucleus and electrons present in various electronic shells. Suppose we have an incident photon of a particular X-ray energy interacting with one of these electronic shells. What happens is that it creates a vacancy because the electron in these electronic shells can absorb this X-ray photon, and then they escape from the atom. Now, there is a vacancy that is created here. The atom is no longer stable. In this process, what happens is that from any of the outer electronic shells, you can have a transition of the electron inwards. And we all know that the inner shells have more energy than the outer shells. As a result, when this transition happens, you can have an X-ray photon of a characteristic energy that is emitted from this atom. So in short, what happens is that we have incident X-ray photons, which cause the ejection of electron from the inner electronic shells. And then, since the atom is no longer in the ground state, you have a transition of electrons from the outer electronic shells inward, in the process emitting characteristic X-ray lines. So the energy of the emitted photons tells us what is the atom. The intensity of the emitted photons tells us how much of that particular atom is present in the sample that we are studying. So in the case of moon, how do we do that? Using class on Chandrayaan 2 is as follows. So we all know that our sun is very bright in X-rays, and we have these high energetic events called the solar flares that happen. So what you see here is an image of sun in X-rays, and you can see that there are these regions of intense magnetic field from where you can have sudden emission of X-ray photons. Now these X-ray photons travel through the interstellar medium and reach the lunar surface. And shown here is the sort of typical spectrum that happens during one of the weaker flares. You can see that there is a continuum and there are these X-ray lines that are coming from the sun. So these X-ray photons are our incident X-ray photons that interact with our lunar surface. And what we have is the characteristic emission that is measured. So it's shown here is an actual spectrum that has been measured using class. And here we can see that there are lines corresponding to various elements of interest. For example, we have oxygen, iron, sodium, magnesium, aluminum, and silicon. So we have been able to identify these lines based on the energy, and the intensity gives us some information of what proportion of these elements are present in the lunar surface. So this is how we actually do retrieve the elemental abundances from our X-ray emissions. So let's first look at what are the pros and cons of using X-ray fluorescence as a technique. So one of the major benefits that we get is that it is a direct approach where we use the fundamental equation. So what this essentially means is that given the intensity, we actually compute it from first principles. So we are able to get quantitative estimates of all major elements. And in our experience with Chandrayaan 2, we see that we are also able to measure certain minor elements. Now, the third major benefit that we have in comparison to other techniques like infrared is that we are insensitive to surface weathering process. It is insensitive to the temperature, crystal structure, maturity of the soil, etc. So while infrared spectroscopy gives you the mineralogy, etc., it is highly sensitive to the maturity of the soil, and it is sort of qualitative in nature. So in comparison, the benefit that we get from X-ray fluorescence spectroscopy is that it is insensitive to any kind of surface effects. However, there are certain limitations. The first major limitation is that the signal that we measure is dependent on the solar activity. So what we see is that when the sun is very quiet, which was the case when Chandrayaan 2 had gone, we don't get a lot of solar flares. So when there are not many solar flares that are happening, our signal from the moon is very limited. Now, the second major disadvantage is that we are measuring the emissions from top few hundreds of microns of the surface. So we are getting only the composition of the regolith. We have nothing, we cannot comment on whatever is the interior structure, etc. And the third major limitation is that the spatial resolution that we get is of the order of tens of kilometers to hundreds of kilometers. So there are solar flares are of different intensities, as all of you might know. So we have very strong flares called X class flares and very weak flares called A class flares. So whenever we have A, B, C class flares, the kind of resolution that we get is of the order of about 150 kilometers cross 12.5 kilometers, while for a very strong flare like an X class flare, we can go down to 12.5 kilometer cross 12.5 kilometer. So to give you some context, if you were to use a technique like infrared, the kind of resolutions that you're talking about is of the order of tens of centimeters. So while we are about an order or two weaker in terms of spatial resolution, but the information that we get is totally quantitative in nature, and no other technique other than gamma ray spectroscopy can directly give you the elemental abundances. So even though gamma ray spectroscopy can also give you elemental abundances, it also has comparable spatial scales of about 150 kilometers. So with that, I would like to talk about our instrument that we worked on, which is Chandrayaan 2 large area soft X-ray spectrometer. So on the right that you see is the actual flight instrument that has flown on Chandrayaan 2. So the energy range that we are interested in is 0.4 keV to 15 keV. This has been chosen so that the lines of major rock forming elements can be measured. The detector that we have used is a swept charge device called SED. It is very similar to the charge coupled device, CCD. So if you all know, CCD actually can capture the photons and can give you the intensity as well as energy of the interacting photons. The difference between an SCD and a CCD is that CCD is capable of doing imaging too, but in SCD, since we are interested in collecting the photons in a fast manner, we do not do imaging. So the image information or the position from which the X-ray photon is coming, that is not captured inherently by the detector, which is why we use something called as a collimator. So a collimator is a module that defines our field of view on the surface of the moon. So here we have copper collimators that have been coated with gold, which give us an instantaneous FOV of 12.5 kilometer cross 12.5 kilometer from an altitude of 100 kilometers. So Chandrayaan 2 is in a polar orbit at an average altitude of 100 kilometers. So from that orbit, we are able to subtend a FOV of 12.5 cross 12.5 kilometers. Now we all know that these silicon devices are extremely sensitive to optical photons, and optical photons are like a noise to our data. So we are interested in photons in the X-ray band. So what we do is use light blocking filters called, so here it's aluminum filters of 200 nanometer thickness. So in this figure, what you see here on top, that is our light blocking filter, below which the copper collimator is present, and this is the detector base plate on which the detectors have been mounted. So you can see that there are four quads present, and in each of the quad there are four detectors. So total we have 16 detectors. Now you also see that there is a door that is present. So this door has been given so that the detectors can be protected from radiation damage as during the trajectory from Earth to the Moon. So like the Earth has a magnetosphere in which there's a lot of charged particles that are present. You know, the Van Allen radiation belts. So we do not want these charged particles interacting with our detector and causing radiation damage. And so to protect from that, we have this door. There's also another purpose for having the door. So we have mounted these radioactive calibration sources on the door. So these are Fe55 sources. Why we do this is that even though we do calibration on ground, we do want to ensure that after the instrument has gone on orbit, everything is all right. So we do use these onboard calibration sources. So that is why we have the door on class. So this is one part of our experiment, right? So we have
Ma'am,
class.
sorry
Yes.
to interrupt,
Yeah,
but
yeah.
we have a question from Pranjal Sengupta.
Okay.
He's asking, do we need to calibrate the observed data from the lunar surface with the corresponding solar spectrum at that time obtained from missions like Aditya?
Yeah, so I am getting there. So see, like I said, it's our solar flare photons that are causing the X-ray emissions from the moon, right? So while we measure the X-rays from the moon, we also need to simultaneously look at whatever is coming from the sun that is causing the excitation, for which we rely on X-ray solar monitor XSM, which is a payload on Chandrayaan 2 that is continuously observing the sun. So shown here is the spectrum that is measured by XSM during different solar flares. So you can see that for X class all the way to A class, the different like so you can see that the solar uh, X-ray photons are highly variable in nature. For example, if you have a weaker flare like an A or a B class flare, it kind of falls off after maybe 3, 4 keV. Whereas when you have a very strong flare like an X class flare, you have emissions all the way up to 10, 15 keV. So what this tells us is that the incident spectrum that is falling on the moon is highly volatile in nature. It's varying. So we have excessive measurements that tells us what exactly is coming from the sun, and then we combine it with the class data which is looking at the moon. So shown here is a sort of long-term light curve that has been measured by XSM. So we see that in the early phase of about 2019, 2020, the sun was fairly quiet. But with time, the solar activity has picked up, and we have had about hundreds of flares that have occurred at various intensities. So this is sort of how we do the measurement. So now I'll get to how we actually model class data and what are the various steps in it. So whenever you do the modeling of any spectrum, there are three components that are very important. The first component is the input. In our case, the input is whatever are the X-rays that are measured from the moon by class. The second input is the incident spectrum, which is falling on the lunar surface. For this, we get the solar X-ray emission from XSM. Additionally, we also need the background. So, as you all know, there could be some particles present in the ambient lunar orbit which could be interacting with the class detector. So, at any kind of any, not just when we look at the moon, any stellar body that you study, there could be some sort of background which always exists in your detector. So, you also need to remove that background component. So, these are the three major inputs. The second aspect that affects our analysis is our physics model. So your physics model is essentially the process that you have to model in order to get the output of interest. So in our case, what the parameters that we are interested in are the elemental abundances of the lunar regolith, right? So for this, the physics model that we use consists of two parts. The first one is the characteristic X-ray fluorescence emission from the lunar soil. Second, we also have the scattering of the solar X-rays by the lunar surface. So the physics model that we use actually accounts for both of these. So the standard software that we use is XSpec, which is X-ray spectral analysis software, which is commonly used not just for this process, it is also used for any modeling of even stellar sources in the X-ray domain. So what it basically does is that it takes a physics model, convolves it with any kind of instrument response, and then does a sort of chi-square minimization to get the model parameters and give us the output. So this is essentially the block diagram of the spectral analysis procedure as a whole. So now let's look at the actual methodology that we employ to do the spectral modeling. So the product that we start off with is the class L1 data. So what we have is the 8-second spectrum, which is giving a footprint of 12.5 kilometer cross 12.5 kilometer of the lunar surface. Now, as I told you, our signal levels are heavily dependent on the kind of solar flare that is occurring. So you may not really see lines with good signal to noise ratio within an 8-second spectrum. So what you need to do is integrate the spectrum in time so that you can improve your signal to noise ratio and can get actual lines which can be fit with high confidence. So this is sort of an iterative process which you need to repeat and put on some, you need to define some like certain thresholds. For example, you need to define that, say, in the energy band of interest, you should have counts greater than 3 sigma of the background. So such sort of thresholds you can set and keep integrating till you get a spectrum which you think is has enough statistics to do spectral fitting. So with this integrated class spectrum, you also need to give the background model. And simultaneously, what we do is that we collect the XSM data corresponding to the solar flare time and corresponding to the class spectrum that we are interested in fitting. And then we apply standard solar models. So usually we use VAPEC or CH-ISOT, etc., which basically models in isothermal plasma. So the corona of the sun from which we are actually getting these X-ray emissions can be modeled as an isothermal plasma, so that then once you're able to model that, you will get the temperature and emission measure of the plasma as well as the abundances of various elements present in the corona. So once this is done, we can actually get the model of the original incident solar spectrum. With that, we convolve it with one component of our physics model and extract what is the expected scattered model spectrum. So these three components are then used into the spectral modeling. So what we use is for the ease, we use PyXspec. This is nothing but a Python wrapper for Expec, and why we do that is because you typically we are dealing with about 10,000s of spectrum. In order to automate the process, we have used PyXspec. But if you're interested, and if you're interested in looking at say one solar flare with probably 10 or 15 spectrum, you can as well do this in Expec. And once we do the spectral modeling, the output that we get is our best fit abundances of the lunar regolith. So I told you, right, that we are observing these background spectrums. So just to give you a context of what this background spectrum looks like. So this is essentially how we arrived at the background spectrum, is that On the day side, we expect that the solar X-rays are exciting some kind of an emission from the moon, even during non-flaring times. So what we did was do a long-term integration of spectrum from the night side of the moon. So there we see there are certain lines corresponding to the different components of our instrument. For example, we have copper collimators, so we see copper K alpha lines. We also have aluminum light blocking filters, so we observe aluminum line. Same way with gold, titanium ion, etc. So we have identified that these lines correspond to the X-ray XRF emissions caused by the interaction of these particles with the various components within our instrument as a whole. So what we have done is we have collected data from the night side for about 9 months of observation, and using that, we have ensured that the background levels are not varying with time. It is fairly constant. As a result, this background can be taken for all kinds of flare analysis. Suppose we see that this background doesn't fit, we also, in certain cases, use either pre-flare or post-flare observations to use as background. But this is the sort of average background that we use. And just to give you some an example of what the spectral modeling looks like, so what you see in blue here is the actual observation by class, and shown in orange is the best fit model that we have got here. So these lines correspond to iron L here. We have magnesium, aluminum, silicon. This is the scattered solar line, and we also have the calcium and calcium K alpha and K beta lines. So this is the actual instrument observation. This is the unfolded model. So what this unfolded model essentially means is that we have removed the instrument contribution from this. And this is what the essential components looks like. So this dark gray color, that corresponds to the scattered solar spectrum. As you if you remember in the first two slides, I had shown what the original incident spectrum looks like, which consists of a continuum and a bunch of lines. So we see that that shape of the continuum has been modified. Additionally, we have the XRF emissions corresponding to these elements of interest. So the data of class can be downloaded from Pradhan website. So at the end of the session, once I've finished the talk, I'll also show you what the Pradhan archive looks like. So all Chandrayaan 2 data is available in Pradhan. So each, you can search the data according to time of observation, the actual lunar coordinates, etc. So this is from where you can download the class data. So just also want to give you an idea of what are the major science results that we have got from class till now. First one is the global maps of major elements. So the primary science objective of class was to create these sort of global elemental maps. So these maps are at spatial scales of 150 kilometers cross 12.5 kilometers. And we have actually released these as an L2 product in Pradhan itself for magnesium, aluminum, silicon, and iron. So there are some very interesting features that you can see here. For example, if you focus on this central region, you see that it is rich in magnesium and iron, whereas it is poor in aluminum. And if you go to this next slide, we can see that there is a sort of anti-correlation relationship between magnesium ion as well as aluminum. And this has something to do with the Mare-Highland dichotomy. So what we know is that the highlands have been formed from the aluminum calcium rich minerals that had floated to the top from the global lunar magma ocean, whereas these mare regions have been formed from the volcanic volcanism that were caused by these sort of impact regions, right? So you had the excavation from the deeper portions of the mantle where you had these iron, magnesium rich silicates that had sunk downward. So since those regions were excavated, we see that the mare are actually very rich in iron and magnesium and low in aluminum, whereas the highlands are rich in aluminum and low in magnesium and iron. So these anti-correlation trends on a planetary scale have been first observed from class. So additionally, since these are at sort of these like sort of coarser scales, now that we have significant amount of data, we are also in the uh, process of preparing these high resolution maps at certain regions of interest. For example, this is a study that which we recently completed and is soon to be published about the high resolution maps at Chandrayaan 3 landing site. So we are able to generate these maps at the scale of about zero point 0.5 degree cross zero point 0.5 degrees. So these are these much finer scale maps which we are able to generate because we have almost more than 4 years of data. Similarly, we also did another study over Theophilus crater. This is interesting because it is there's a smaller crater called Shioli, which is closer to it, over which the Japanese mission SLIM had landed. So we see that this is an interesting region to study because it is at a sort of confluence between the highland as well as the Mare region. And we see that from class data, there's something called a buried mare. So it's called a buried mare because the volcanic deposits there have been overlaid by further highland ejecta. So these were not really showing up in other data sets like IR mineralogy, etc. But from class data, we are actually able to see that over the buried mare, the composition is as expected from Mare region, which is basically higher amount of magnesium and lesser amount of aluminum. So we are now going towards creating these sort of high resolution maps. So few of the other regions that we are working on are like Mare Imbrium, Mare Crisham, etc. And these are all regions where there has been prolonged volcanism. So such kind of studies are also possible to do with class. So this is where we are coming to here. So another interesting parameter which can tell us a lot about the kind of volcanism is magnesium number. So this magnesium number is defined as magnesium by magnesium plus iron. Why this is important is that we know that most of these magnesium ion silicates are nothing but solid solutions. And since the cationic size of magnesium and iron is very similar, they can replace each other in these crystal lattices. So what essentially happens is that when you have molten magma with a certain proportion of magnesium and iron, as it cools down, the minerals that crystallize will be of varying compositions. For example, magnesium silicates have a much higher melting point, and hence these will be the first to crystallize out, whereas iron rich minerals start crystallizing as the temperature falls much lower. So, what our current understanding is that if the Mare unit is much older, it will have a higher magnesium number, whereas the younger Mare regions should have a lower magnesium number because they will be more rich in iron. So what we did was from these global maps itself, we extracted the magnesium number, compared it to the age estimates from crater counting chronology. So crater counting chronology is a technique that has been applied to retrieve the age of lunar surface features. So what they essentially do is that from the image data of the lunar surface, depending on how much or how heavily cratered it is, you can get an estimate of what is the age of the surface. So an older surface, which would have been exposed for a much longer period of time, would be heavily cratered in comparison to a younger surface, which would have been exposed for much lesser amount of time and therefore would be much less cratered. So using that, there have been estimates for age of these different geological units. And so what we see is that we actually see this trend where the younger Mare regions have a lower magnesium number than the older Mare regions. However, you can see that there is a wide range that we observe. Now, this we feel could also indicate that there could be multiple mantle reservoirs. So, as you all know, various Mare regions have been formed from impacts that occurred at different points of time. As a result, we can claim that they have tapped into the mantle at different points of evolution in the lunar history. So, as a result, the composition of the source, that is the mantle reservoir from which this mare has been retrieved, might have been evolving. So, while not much can be said from these sort of global estimates, we suspect that if we generate these high resolution maps over certain regions and then study this relationship, we might actually able to get more information, and we can also get some idea about the condition of the mantle. So that is a sort of very powerful thing to say, because you don't really have mantle samples from the moon except till date. So if you can apply some kind of these indirect indicators for what could be representative of the mantle composition, it would be a very useful information to have. But this requires quite a bit of modeling to so what we do is assume an average composition for the global lunar magma ocean, apply the temperature, pressure, evolution constraints, and then extract what would be the stratified layers of the moon. So with that, what we can say is that for a given composition that we measure at the surface, from what depth has it been excavated, we can estimate. So with that, we can say what something about the mantle. So this is the kind of study that we are targeting to do. Additionally, we have also studied these minor elements like chromium and manganese, which from return samples have been observed, but they are of the order of ppm level. So we do see that even though class is applying X-ray fluorescence spectroscopy from a remote sensing platform, in spite of that, we are actually capable of detecting these sort of minor elements which are present in the order of hundreds of ppm. And similar to this, another interesting study that we did was the distribution of sodium. So from return lunar samples, the average sodium weight percentage is of the order of a few hundreds of ppm. But what we observed using class was that we were able to get a much higher value of an average abundance of 1.33 weight percentage. And we were actually able to make a sort of global map of sodium, which has not been done till date. And in addition to that, what we did was we tried to study the variation of sodium with the local solar time. So what we see is that closer to dawn and dusk, our sodium abundances increases, whereas as we approach closer to the noon time, our sodium abundances are at the minimum. So this gave us a hint that this could be because sodium not is not just present as a geochemical component, it could also be as an adsorbate layer. So even from ground-based telescopic measurements looking at the exosphere of the moon. So we all know that moon does not really have an atmosphere. What it has is a surface bound exosphere. So we do expect that the sodium atoms present in the surface bound exosphere could be constantly interacting with the surface, and there is an active process where the atoms from the exosphere are adsorbed onto the surface, and there vice versa too, where they are lost from the surface to the exosphere. So we do see that the high weight percentage of sodium that class measures can actually be due to the adsorbate layer. So in this paper, what we did was we modeled the adsorbate layer, and we were able to retrieve the average thickness for this adsorbate layer. That was also something interesting which we were able to do with class that has not been done in any other waveband using any other instrument till date. In addition to this, though class was intended to study the surface composition of the moon, we also observed something very interesting. So, Earth has a geotail, and we know that moon passes through this geotail once every month. When that happens, the ambient particles in the geotail deposit a lot of energy on class detectors. So, when we looked at the light curve over about a year or two, what we see that whenever the moon passed through the geotail, we were able to see these sort of enhancements which were caused by the interaction of these particles. So then we were able to model and understand that these interactions were primarily caused by low energy electrons present in the Earth's geotail. So this is sort of an average over about two years of data. Additionally, we also saw that whenever there is some CME or some solar energetic event, we were able to see like those particles were also interacting with the class detectors, and we were able to measure the light curve. So GOES is in a geostationary orbit around the Earth. So when the CME was captured by GOES, simultaneously we see an enhancement in the counts that was observed by class 2. So with that, I hope that you were able to get a sort of overview of what essentially X-ray fluorescence spectroscopy of the moon entails and what class as an instrument is capable of doing. So I would uh, hold on. So I would just quickly like to show you the Pradhan website. So in Pradhan website, you see that I'm sorry. Is the web browser visible to everybody?
Yes, ma'am.
So in the Pradhan website, you can actually see that the data of all the Chandrayaan 2 missions is available. So when you go into class, you can search the data depending on the observation time. You could define a polygon of your region of interest, and then it will filter out this data. So this is the L1 product at a spatial resolution of 12.5 kilometer across 12.5 kilometer. So you could also uh, do it on the basis of the processing level. Additionally, if you want to process class data, you also need other instrument parameters, right? So the calibration files are available in the other downloads. And we also have the, we- Hello, am I audible?
Yes,
Yes,
ma'am.
ma'am, you
Yes.
are audible.
Yeah, so the local model that we use to actually model class data is also available as a zip file. So this is where you can, like, this could be a good point for you to start off analyzing class data. So I'll be happy to take any questions.
Ma'am, we have a question.
Okay.
The question is, why is the chemical composition of moon so different when compared to Earth if they were formed from the same thing?
Because you also have a component that has been caused from Thea, right? So some component of Thea should also be present. Also, when the average composition of the Earth, when you say it is the crust, mantle, and the core. So when the impact had occurred, a large portion of the Earth's crust and the mantle was excavated. So what you see in the moon is slightly different because the core of the Earth is not it was not excavated during the collision. So if you see for the moon, the iron nickel rich core is much smaller. So I hope that answers that.
Thank you, ma'am.
Any other questions, participants? We can also unmute you if you want to discuss something. Ma'am, we have another question.
Okay.
Pranjal is asking, do we need to calibrate the signal for the different position of the moon when it passes through the geotail?
Okay, so currently what we do is that we do not use the data during geotail because it is very difficult to actually model the particle contribution. So the way that our detectors respond to X-ray photons is fairly easy to model. So that is present in the calibration file. But how the detectors respond to the ambient particles in the geotail is very difficult to model, and geotail is very volatile in nature. So around the full moon time, plus minus 3-4 days, we recommend that you don't use that data for any kind of surface composition based studies. But any other time, if you want to look at the calibration files available in Pradhan, basically there are two files for instrument response. One is called as the redistribution matrix file that basically tells you how the energy of the incoming X-ray photon is redistributed within a detector. And then you also have a file for the quantum efficiency of the detector. So with these two files, you can actually model the response of the instrument and remove it from your spectral modeling analysis. So this procedure, even if you were, I mean, I'm not sure how many of you have actually done the X-ray spectral modeling, even for stellar sources. So if you have done that, you would be familiar, if any of you are familiar with XSpec and how you do it. So you have these models which are defined inside XSpec, and then instrument responses are typically stored in RMF and ARF files. So those are available in the other download section in Pradhan. The model is also available. So geotail time might not really be suitable for surface composition analysis, but the rest of the flare times are usable.
Thank you, ma'am. Pranjal is again asking, is the volatility of the geotail responsible for the arbitrary amount of amplification of the signal in the geotail?
Yes. So if you see, like, if you were to, I mean, I didn't zoom in, but if you were to zoom into any of these, like each one corresponds to one full moon time, the kind of oscillations that you see are much higher. They're of the period of millisecond, like millisecond to second, one a few seconds. So it's very difficult to predict. And what we see is that from one geotail to the next, the signature is not same, and you can also see a sort of a sort of sinusoidal variation across 2 years. So currently, one of my co-workers is working on this as a part of his PhD too. So this is something we're still studying and evolving towards.
Thank you, ma'am. We have another question from Lalit. He's asking, there will be background X-ray radiation from all parts of the universe, right? So how do we remove all that to collect specific data we want?
Okay, so first thing is to visualize what the orbit is like. So we are an instrument where our FOV is constrained by our collimators, which are mounted here, right? So we can only view about 14 degree cross 14 degree on the moon surface. So in astronomy, what you typically do is that you have, even though you have an FOV of a few degrees, you are actually capturing, like the stellar sources are typically point in nature. So you capture multiple sources within your FOV. But from 100 kilometer polar orbit, moon is an extended object, and we are only viewing a portion of the moon. So cosmic X-ray background is not really a problem for us.
Ma'am, we have another question from Siddharth. He's asking, the chemical composition of near side and far side are similar or completely different as they were alloy of volcanic activity in near side.
Yeah, correct. So the we know that the near side of the moon has a much higher volcanic activity, and therefore it has much more mare regions. So this is a photo of a near side. So the far side is much more highland in nature. So if you see these global maps, you can actually, so this is roughly the near side, and the far side has the typical highland composition with higher amount of aluminum and lesser amount of magnesium and iron. So we do see that compositional dichotomy between the near side and far side.
Thank you, ma'am. Any other questions? I think that was it. Thank you, ma'am, for this wonderful session. We deeply appreciate your time and effort. I'm sure all of us learned a lot.
Yeah, thank you. Thank you so much. So, just want to tell all of you that planetary is something that's budding within the country. So, it's nice to see people with an astronomy background branching into planetary. So, all Chandrayaan 2 data is publicly available within Pradhan. Please feel free to download the data, try exploring, and any kind of questions that you run into, even in the future, feel free to drop in a mail to either me or Shama ma'am, and we'll definitely get back to you. So this is a data set that's not been explored by a lot of groups even in the world. So there's very few groups who actually do X-ray spectroscopy of planetary targets. So this is something interesting, which I'm hoping if any of you who've like listened to this talk and are interested, please do go back to Pradhan, download this data, and any kind of help that you need, there's user manual too, which is pretty self-explanatory. But in case you guys run into any issues, feel free to reach out. So yeah, it was a good session and good questions too.
Thank you very much, ma'am. Excuse me, ma'am. Participants are asking for your email. Can you please drop it in the chat, maybe?
Yeah, sure.
Also, we have another question.
Mm-hmm.
Pranjal is again asking if the far side is exposed to less volcanic activity, shouldn't we expect to find more mere composition there?
Okay, so right. So if we can go back to this, the presentation is visible, right?
Yes,
Uh,
ma'am. Yes.
yeah. So see, there was a global lunar magma ocean from which these iron, magnesium-rich minerals actually crystallized and they sank. So this is what we understand today as our mantle, lunar mantle. And then you have these calcium aluminum rich silicates that were less dense and floated on top. Now, what happens when you have an impact is that you have the excavation of these inner materials which come back onto the surface and then form the mare regions. So, on the near side, you've had much more volcanic activity, so you have the excavation of these deeper regions and the mare formed at the surface. But on the far side, since we've had less impacts and so less volcanic activity, what you see is the sort of primordial or original highland feldspathic crust, which is rich in calcium and aluminum. So it's actually the other way around. So where you have less volcanic activity, you find more of this crust. Where you have more volcanic activities, where you find more of the mantle related features.
Okay. Thank you, ma'am. The participants are expressing their thanks in the chat.
You.
Thank you. So, thank you all for joining us for this workshop. We'll drop a Google form in the emails. Please fill it as a feedback form so that if we plan to organize a workshop of this sort, we may have your opinions. Thank you all for joining us and have a good day.